Analyzing temporal data requires understanding the underlying state of a system, but in many physical and digital environments, the actual governing reality is completely hidden from view. We cannot measure it directly. Instead, we are forced to measure secondary, noisy effects. If we want to know the true weather conditions in a remote location, we might only have access to ground-level observations, like whether a local resident is carrying an umbrella or wearing sunglasses. A single observation in isolation tells us very little. Someone might wear sunglasses on a cloudy day or carry an umbrella out of habit. The true nature of the hidden state only becomes statistically detectable when we analyze the specific sequence of these observations over time. To predict how a sequence will unfold, we have to mathematically decouple the hidden driving mechanism from the observable evidence. We need a framework that defines exactly how the unseen generates the seen. This specific statistical framework is called the hidden Markov model. Developed in the late 1960s and 70s, it was engineered specifically to solve the unobservable state problem. Standard neural networks and support vector machines often require fixed-size inputs. Hidden Markov models bypass this limitation entirely. They naturally process sequences of varying lengths, adapting to the actual span of the data. There is one strict requirement. The exact order of the sequence must be preserved. The observations cannot be randomly shuffled, because the passage of time is the primary relationship the model evaluates. We are going to explore how this model uses transition and emission probabilities to map temporal dynamics, and exactly how an algorithm known as Viterbi decodes the final sequence. By isolating the hidden variables from the visible evidence, the hidden Markov model standardizes the relationship between time and probability, allowing for the exact inference of hidden sequences. Calculating exact probabilities across massive timelines naturally creates a combinatorial explosion. To keep the math computationally feasible, the model relies on two foundational constraints. The first is the Markov assumption. This rule dictates that a future hidden state depends solely on the immediately preceding hidden state. It explicitly ignores deep historical data. Tomorrow's state is calculated using only the data from today. The second constraint is the sensor independence assumption. This dictates that an observation recorded at a specific time depends entirely on the hidden state occurring at that exact same microsecond. It isolates the evidence to its exact moment of origin. Together, these assumptions slice an infinitely complex historical timeline into a computationally viable chain of immediate, step-by-step relationships. With the timeline constrained, we can build the actual architecture. The model is defined by three core parameters, collectively represented by the Greek letter lambda, which the system learns from training data. This equation illustrates the joint probability of a sequence. The first variable is the initial state distribution, denoted as pi. This is the baseline probability of the system starting in any given hidden state at the very first time step. Next is the transition matrix, or A. This grid contains the explicit probabilities of moving from one specific hidden state to another as time ticks forward. Finally, the emission matrix, or B. This defines the exact probability of observing a particular piece of evidence while the system is locked in a specific hidden state. The full equation multiplies the starting probability by the initial emission, and then sequentially chains every subsequent transition and emission up to the final time step, big T. This single structure solves three operational problems. It handles evaluation using the forward algorithm, learning via the Baum-Welch algorithm, and decoding. These matrices establish the concrete physical rules governing the system's behavior. Once they are set, we have everything we need to decode a hidden sequence. Decoding is the process of uncovering the most likely sequence of hidden states, given a known observed sequence of evidence.
For sequences of any real length, calculating every possible historical timeline to find the right one is mathematically impossible. The variations outnumber the processing power of modern computers. To solve this, we use the Viterbi algorithm, a dynamic programming technique built specifically to chart the optimal path through a vast network of probabilities. By calculating the best local path at each step and discarding the rest, the algorithm bypasses the need to evaluate the entire universe of possibilities. This diagram represents a trellis structure. The columns map the sequential time steps from t equals 1 to big T. The rows map the potential hidden states. Every intersection is a node. We begin at time step 1. The algorithm calculates the starting probability for each hidden state, factoring in the immediate emission of our first observation. Moving to time step 2, we execute a forward recursion. For every possible current state, the algorithm looks backward at all possible previous states. It calculates the cumulative probability of arriving at the current node from each of those previous locations. Here is the crucial optimization. At each node, it identifies the single path with the maximum probability. It then permanently discards all lower probability routes. For the winning path, it saves a backpointer, a strict record of exactly which previous state yielded this maximum score. We repeat this recursive process. Calculate, discard, and point backward for time step 3, time step 4, all the way to the final column. At termination, time step big T, we simply select the single hidden state node holding the highest overall accumulated probability. Finally, we backtrack. We follow the saved pointers from that final node all the way to the beginning. That continuous line is our optimal sequence of hidden states. The Viterbi method guarantees the discovery of the mathematically optimal sequence, and it does so without ever recalculating a redundant historical path. Once a model is trained, we have to evaluate its accuracy. We start with log likelihood, a metric that calculates exactly how well the mathematical parameters explain a fresh set of test sequences. If we already know the true hidden states, like when testing a part of speech tagger, we measure sequence accuracy. This outputs the exact percentage of time steps where the model correctly predicted the reality. In natural language processing, engineers use perplexity to grade how accurately the model anticipates the subsequent item in a chain. These metrics highlight the model's distinct advantages. It accommodates sequences of any arbitrary length and relies on exact mathematical inference rather than approximation. Furthermore, compared to dense neural networks, the hidden Markov model is highly interpretable. Human operators can literally read the transition matrix to understand the explicit rules driving the system. However, the mathematical constraints that make the model fast also limit its scope. The Markov assumption is often false in practice. Real-world futures depend on deep historical context, meaning this model operates without any real long-term memory. It also suffers from state-space explosion. Increasing the number of hidden states causes the transition matrix to grow quadratically. This demands massive amounts of training data and heavily increases the risk of overfitting. When trained using unsupervised methods like the Baum-Welch algorithm, the model is highly sensitive to initialization. A poor starting point can leave it permanently trapped in suboptimal configurations. Despite these limitations, its architecture provides the foundational logic for sequence tagging in several fields, translating audio waveforms into spoken words, discovering gene structures in unmapped DNA, and tracking shifting market regimes. Even with strict memory constraints, the hidden Markov model provides an elegant, rigorous method for piercing the noise of time and extracting hidden realities.